Before we start today, let's just run through some examples of space travel and decide if it's between planets or planetary, between galaxies or intergalactic, or if it's going to another dimension. Intergalactic. Planetary. Planetary. Intergalactic. Another dimension. Another dimension. Another dimension. Hang on, how the hell did this one get in here? No. Splashing some water and some, wind in my face is not another dimension. Okay, it seems like I care way too much about that nonsense. Let's get on with the actual video. Right then, space travel in sci-fi has always had a complicated relationship with science. And by complicated, I mean is forced to ignore it completely so that storytelling is actually possible. Take Star Wars. They zip around their galaxy in a matter of minutes? Hours? Days? They don't ever really clearly state it. And for good reason, it'd detract from the plot. And now they've gone and decided to explore another galaxy. They talk about needing to run the calculations to get there and how it's much more complicated than normal hyperspace travel. But they don't go into any more details about the calculations than that, assuming the audience isn't all that fussed about letting numbers ruin some perfectly good Star Wars. But weirdos like me, and hopefully you, seeing as you've stumbled onto this video, want to explain a little bit about why extragalactic travel is so different. Side note, if you are one of the crazy people who likes mixing science and science fiction, consider clicking the subscribe button. You'll get some answers to how things work in your favourite films and shows, but I'll bear the burden of the insanity induced by crunching all the numbers for you. So there's two big things to keep in mind when it comes to space travel. 1. Space is very big. And 2. Space is mostly nothing. So to illustrate that first point, let's take the diameter of the Earth. That distance is 0.0085% of the distance from the Earth to the Sun. Now take that distance, known as one astronomical unit. That is 0.00039% of the distance to the next nearest star, Proxima Centauri. Now that distance is approximately 0.0038% of the diameter of the Milky Way. See how small these numbers are getting? And we haven't even left the galaxy yet. The diameter of the Milky Way is only about 4% of the distance to the next nearest galaxy, Andromeda. So space is huge. But those giant gaps between stuff are filled with stars and planets and all sorts of other interesting stuff that all added together account for around 0.00000000000000000000000000042% of the total volume of the universe. Also, yes, I had to count the zeros on my fingers as I was reading that out just to make sure I got it right. Yeah, everything is mostly nothing, both in terms of space mostly being devoid of matter and the matter itself being mostly empty. But that second one is a story for a video I already did. But what does this mean for space travel? Well, in real life, it means that it takes a really long time to get anywhere. In reality, it takes about 3 days just to get to our own moon. Obviously, how long it takes to travel is dependent on how fast you're moving. The fastest a human has ever travelled is 11.08 kilometers per second, which is around 40,000 kilometers an hour or 25,000 miles an hour, which was during the Apollo 10 mission. This is still only around 1/27,000th of the speed of light. And even light isn't that fast relative to the size of the universe. It takes over 100,000 years to traverse the diameter of the Milky Way, and takes 2.5 million years to reach us from Andromeda. Back to Star Wars then. For the characters to be zooming around their galaxy in a matter of days, means they must be travelling faster than the speed of light. And what does physics have to say about that? No, just no, don't. Physics says no. Hyperspace travel inherently can't have a true rooting in physics, but even though parts of it could have some interesting concepts to explain, this is supposed to be a Star Wars video, so I'll actually steal the line from a certain stick figure and call it a story for another time. With all that, why is extragalactic travel so complicated? Well, let's quickly catch everyone up to speed on what happened in Ahsoka. So without going over the entire plot of the series, because I don't think I've quite got time to cover that here, let's just explain what part that we're actually looking at. So we see the bad guys in Ahsoka travel from Cetos, in the Star Wars galaxy that we've known for decades, to Peridia, a planet in a completely separate galaxy. So they seem to use just a scaled up version of the usual hyperspace travel, and take a lot longer to run the calculations to figure out how to get there. But let's assume for the sake of simplicity that it's a straight shot from Cetos to Peridia, and let's use the distance from the Milky Way to Andromeda as our guide, which is 2.537 million light years, or 24 sextillion meters. Now then, it's time to figure out everything that could go wrong. Wait, what do you mean angles? We've just said we're going in a straight line. But what if we point that straight line 1 degree in a different direction? So if we travel 24 sextillion meters in this direction, we're good. But if we move that line 1 degree to the right, how far away are we? Well, it doesn't look much relative to the 24 sextillion meters, but let's just exaggerate it for a second so we can label some parts. So we've got ourselves a triangle where we know some things, but we want to figure out other things. It's time to use some... Honestly, that is probably the most exciting I can make trig sound. But specifically, we know the length of 2 sides, and the size of the angle between them. We want to know the length of the third side, so we need to use the cosine rule, which looks like this. If you're not sure what this thing here is, it's the trigonometric function called cosine or cos. Basically, you plug in an angle, and it gives you a ratio between 0 and 1 that relates to the triangles in various ways. In this scenario, we're plugging in 1 degree to help us get the ratio between the sides of this triangle. Plugging all the numbers here into the cosine rule, it gives us a distance of 420 quintillion meters, or 45,000 light years. To put that in perspective, that's about 43% of the diameter of the Milky Way. So if the Eye of Sion here is pointing 1 degree in the wrong direction, it'd end up on the other side of an uncharted galaxy, nowhere near Peridia. Right, we've been acting like we've been moving between static places here. Everything in the universe is moving relative to each other. Let's take Earth as the example. We're moving at around 30,000 meters per second around the sun, but then the entire solar system is moving around 200,000 meters per second around the center of the Milky Way. Add on to that, galaxies are all moving relative to each other as well. Most galaxies move away from each other as the universe expands, however closer galaxies move together due to the force of gravity. Andromeda is moving towards the Milky Way at about 300,000 meters per second, and in about 4.5 billion years, the two galaxies will actually collide with each other. So trying to plot a route to another galaxy will depend heavily on when you start the journey. If you plot a route from Earth to somewhere in the Andromeda galaxy, then leave 1 second later, Earth has moved 30 kilometers relative to the Sun, which has moved 200 kilometers relative to the center of the Milky Way, which has moved 300 kilometers closer to Andromeda. Plus there's a small amount of sideways movement between Andromeda relative to Earth, and all of these movements are completely independent from each other. Okay, when we're talking kilometers, it's not quite as much of a dramatic problem as the angle, but when there's that many independent moving parts, it complicates it quite a bit. We're not talking other side of the galaxy, but we could be talking about accidentally crashing into the planet rather than arriving in orbit. Right, we're assuming faster than light travel is okay for this one. I know, it pains me too, but we're just going to have to put up with it for once. So they zip around their own galaxy in a matter of days, but how long would it take to travel to another galaxy? Well, first we'll need to establish speed. How fast is normal hyperdrive? We don't know. So we're going to have to guesstimate. Again, they don't want to say these numbers just for plot reasons. They want it to take as long as the story needs it to take. But let's assume that it takes a week to travel from one end of the galaxy to the other. The main Star Wars galaxy is supposedly 120,000 light years across, which is slightly bigger than the Milky Way. This gives us a speed of roughly 17,000 light years per day, and trust me, we're better off leaving it in these units. If we were to translate that directly to an intergalactic distance, for sake of convenience, let's use the distance between the Milky Way and Andromeda again. You'll get a travel time of 148 days. Yeah, that's quite a long time to travel in a normal ship, but look at the Eye of Sion. That is not a normal ship. That thing's bloody massive. There's a reason they had to make a special hyperspace ring thing to do the journey. I don't think a regular ship could store the energy required for nearly 5 straight months of hyperspace travel. But just how big is the Eye of Sion? Well, it was equipped with 3 hyperdrive core clusters, or as Wikipedia puts it, 7 SSD classed, which I'm going to take to mean the equivalent power of 7 superstar destroyers. Thanks, Wikipedia! So we'll divide that 148 days by 7, remembering we are guesstimating big time here, to give us a more reasonable travel time of about 21 days. It does also seem like the speed of a Purgil is similar, and if the choice is between a prison cell or story time with Huyang, I think I know which one I'd prefer. Then again, the looming threat of maybe getting swallowed by a space whale might make that ride a little bit less enjoyable. But there you have it, that's just some of the reasons why they have to run all those calculations for an extragalactic hyperspace jump. There'll be a plethora of other intricacies and estimations you can make breaking it down, so feel free to discuss some of those in the comments section. And while you're down there, make sure to click that subscribe button before you get distracted by another video our algorithmic overlords have found for you.